And today, the mind-blowing discovery that's rocking everyone's world is a type of neural network called a transformer. Transformers are models that can translate text, write poems and op-eds, and even generate computer code. These have been used in biology to solve the protein folding problem.
So basically, neural networks have a lot of architectures that were trendy, have come and gone for different sensory modalities, like for vision, audio, text. You would process them with different looking neural nets. And recently, we've seen this convergence towards one architecture, the transformer. And you can feed it video, or you can feed it, images or speech or text, and it just gobbles it up. And it's kind of like a bit of a general purpose computer that is also trainable and very efficient to run on our hardware.
Attention is all you need paper from Google Brain team in 2017 where transformers were introduced. The meme titled "It took internet by surprise, but it did its work." Since then, transformer models have been shown to achieve state-of-the-art performance on a wide range of natural language processing tasks, such as language translation and text summarization. One example of this is the BERT model, which stands for Bidirectional Encoder Representations from Transformers. BERT is a transformer-based model that has been trained on a massive dataset of text and can understand the context of a given phrase or sentence in a way that was previously not possible. This has led to significant improvements in various NLP tasks such as question answering and named entity recognition. A transformer model is a neural network that learns context and thus meaning by tracking relationships in sequential data like the words in this sentence. That architecture produces a model that can be trained to read many words, a sentence or paragraph, for example, pay attention to how those words relate to one another and then predict what words it thinks will come next. Let's hear from Martin Keen how transformer model work.
Well, transformers consist of two parts. There is an encoder and there is a decoder. The encoder works on the input sequence and the decoder operates on the target output sequence. Now, on the face of it, translation seems like little more than just like a basic lookup task. So convert the Y here of our English sentence to the French equivalent of pourquoi. But of course, language translation doesn't really work that way. Things like word order in terms of phrase often mix things up. And the way transformers work is through sequence-to-sequence learning, where the transformer takes a sequence of tokens, in this case words in a sentence, and predicts the next word in the output sequence. It does this through iterating through encoder layers. So the encoder generates encodings that define which part of the input sequence are relevant to each other, and then passes these encodings to the next encoder layer. The decoder takes all of these encodings and uses their derived context to generate the output sequence. Now, transformers are a form of semi-supervised learning. By semi-supervised, we mean that they are pre-trained in an unsupervised manner with a large unlabeled dataset, and then they're fine-tuned through supervised training to get them to perform better. Now, in previous videos, I've talked about other machine learning algorithms that handle sequential input like natural language. For example, there are recurrent neural networks, or RNNs. What makes transformers a little bit different is that they do not necessarily process data in order. Transformers use something called an attention mechanism. And this provides context around items in the input sequence. So rather than starting our translation with the word "why" because it's at the start of the sentence, the transformer attempts to identify the context that bring meaning in each word in the sequence. And it's this attention mechanism that gives transformers a huge leg up over algorithms like RNN that must run in sequence. Transformers run multiple sequences in parallel. And this vastly speeds up training times.
So we know the main concept in transformers is self-attention. But what does it really mean? Let's look at an example. So let's say she poured coffee from the pot to the cup until it was full. So we know it here refers to the cup, while in the sentence, she poured coffee from the pot to the cup until it was empty. Here, it refers to the pot. Meaning is a result of relationship between things, and self-attention is a general way of learning relationships.
Some popular models that use transformer architecture in the background include BERT, which we have already covered. Another popular one is GPT, which is generative pre-trained transformers that is trained on a large corpus of text data and is used for language modeling and can generate human-like text. Another popular one in T5, a text-to-text transfer transformer model that is trained to perform a wide range of text-based tasks, such as translation, summarization, and text classification. Reformer, the efficient transformer, an autoregressive transformer model with lots of tricks to reduce memory footprint and compute time. Electra, efficiently learning an encoder that classifies tokens accurately, is a transformer-based model that is trained to distinguish between real and fake token. Gato from DeepMind is a deep neural network for a range of complex tasks that exhibits multimodality based on transformers. And tons more.
The world is going gaga over the recent release of ChatGPT and DALL-E 2 from OpenAI. Similarly, there has been models like Point E and generative models from NVIDIA. Recent release of VALLE from Microsoft, Imagen, and tons of other models, including Stable Diffusion. But do you all know that the real brain behind all these advancements, the background of these models, are the transformer models?
In this video, we've covered the basics of transformer models and their applications in natural language processing, NLP, tasks. We've also taken a closer look at some popular transformer-based models, such as BERT, GPT, Roberta, T5, XLNet, Albert, and Electra, and the various use cases they have been used for. With the increasing importance of NLP in today's technology landscape, understanding transformer models and their applications is crucial. We hope that this video has provided a solid foundation for you to start experimenting with transformer models in your own NLP projects. For further learning, we recommend checking out the original papers on transformer models, as well as tutorials and pre-trained models that can be fine-tuned for specific tasks. We encourage you to share your results and feedback as you work with transformer models. Thank you for watching, and we'll see you in the next video.